Hi everyone and welcome. It's great to be here at KubeCon Atlanta. I'm Abhishek and I'm here with my colleague Shiva. We are software devs at Google working on the gRPC team. Over the next session, we are going to walk you through the entire security journey, starting from the basics of TLS, moving through the operational challenges in Kubernetes, and finally looking at advanced solutions like service mesh and proxyless gRPC. Cool. Before proceeding, just a short disclaimer. The content and views presented during this session are our personal views and do not represent any organizations we are associated with or employed at. Let's start. To set the stage, let's look at the two technologies during this conversation, microservices and gRPC. We have moved away from large monoliths to building systems as suites of small independent services. And for these services to talk to each other, gRPC has become the industry standard. Why? Because it's a high performance and built specifically for this environment. It runs on HTTP2 for efficiency. It uses protobuf for lightweight serialization and supports bidirectional streaming out of the box. It's the perfect glue for a microservices architecture. But this architecture introduces new risks, especially in Kubernetes. First, it's dynamic. Pods come and go. IPs change constantly. You can't rely on static firewall rules. Second, it's usually a flat network. By default, any pod can talk to any other pod. If one service is compromised, the attacker has a clear path to everything else. This is why we need end-to-end security. We need to ensure that we trust exactly who we are talking to, regardless of the network. Cool. The baseline for this trust is TLS. It gives us three things. Authentication, which is verifying the server. Encryption, so no one can snoop on the wire. And integrity, so no one can tamper with the data. Most of you know this, but in gRPC, these three are absolute non-negotiables. All right. In code, it looks something like this. On the server, which is on the left, we load the certificate chain and private key. This proves the server's identity. On the client, which is on the right, we load the CA certificate. This tells the client which authorities to trust. So, does this configuration help solve all our problem and we can move on with our lives to more important things like collecting swags? Sadly, no. While this is simple enough for one service, we need to go further. MTLS. The standard TLS only protects the client. The server will still accept connections from anyone. For true zero trust, we need mutual TLS or MTLS. In MTLS, the server also verifies the client. Both sides present certificates. This ensures that only authorized microservices can establish a connection. But MTLS creates a massive operational headache in Kubernetes. Think about it. You have hundreds of pods. How do you generate a unique cert for every single one? How do you get that private key onto the pod securely? And critically, how do you rotate them every 24 hours without downtime? Doing all this manually is next to impossible. So what's the solution? The community solution is Cert-Manager. It's a Kubernetes operator that automates issuance and renewal. It treats certificates as first-class resources in the cluster. It connects to backends like Vault, Let's Encrypt, or your own internal CA, and handles the certificate lifecycle for you. Let's see how one works. The workflow is simple. You define an issuer, which represents your CA or the certificate authority. You create a certificate resource or a CRD that asks for a specific domain. Cert-Manager talks to the issuer, gets the certificate, and saves it as a standard Kubernetes secret. Here is what that looks like in practice. On the left, the certificate CRD. We ask for my gRPC service and tell it to store the result in my gRPC server TLS. On the right, in our deployment, we simply mount that secret as a volume add /cert. Now, the files tls.crt and tls.key essentially appear on the pod's file system. Cool. So the full Kubernetes native flow is deploy Cert-Manager, create your issuer, request the certificate, and mount the secret. And also, you need to update your app code to read from that file path. So what's the best part with this? When the certificate is about to expire, Cert-Manager renews it, updates the secret, and Kubernetes also updates the file inside the pod. Your app just needs to watch the file and reload. Okay, so MTLS gives us service identity. The checkout service knows it's talking to the payment service. But what about user identity? Who's the human or the external entity making this request? Is it Alice? Is it Bob? We don't know. MTLS doesn't tell us that. For that, we move up the stack to application authentication. Usually via JWTs or JSON Web Tokens, or also known as JWTs. The client authenticates with an identity provider like Google or Okta and gets a signed JWT. It attaches that token to the gRPC metadata headers. The server then verifies the signature, extracts the claims like user ID to authorize the actions. But please, don't write this logic in every single function. Please use interceptors. They are essentially middleware for gRPC. You write a server-side interceptor that intercepts the header, validates the token, and populates the context with the user ID. If the token is invalid, the request is rejected before it ever reaches your business logic. Here's a quick note about OAuth2. OAuth2 is the protocol for how you get the token, which we discussed in the last slides. The JWT is the token itself. In this architecture, your gRPC service acts as a resource server. It doesn't care how you got the token. It just verifies that the token allows access to this resource. Cool. We have built a secure system, but let's look at the cost. Look at the burden on the developer. Every service needs code to load certificates. Every service needs hot reload logic for rotation, and it also needs JWT validation code. If you have services in multiple languages like Go, Java, and Python, you are writing and maintaining this security boilerplate 3 times. It's brittle. This is where a service mesh like Istio shines. It moves these problems from application layer to the infrastructure layer. It injects a sidecar proxy, Envoy, next to every container. Your app just talks to localhost, and proxy handles all the heavy lifting. With Istio, you get MTLS with 0 code changes. You apply one YAML file to enable strict MTLS. Your app sends plain text. The sidecar intercepts it, encrypts it, sends to the other sidecar, which just decrypts it and passes it to the destination app. Istio handles all the issuance, rotation, and verification automatically. It also revolutionizes authorization. Instead of if user equals admin in your code, you write an authorization policy YAML. You can say only the front-end service can call /getUser method on the backend service. The proxy enforces this. Unauthorized traffic never even touches your application. And yes, it handles JWTs too. Using a request authentication policy, the proxy validates the JWT signature and issuer. If the token is bad, the proxy returns a 401. Your app only sees valid requests. We have successfully deleted all that boilerplate security code. So, Service Mesh seems perfect. It solves operational headaches, improves security. But there's a cost. That sidecar proxy adds a network hop. Now, for majority of our apps, this might not be an issue. But for hyperscale or real-time services, that latency adds up. So we have to ask, can we get all these benefits, the security, the management, the dynamic configuration, without the sidecar penalty? Is there a way to be faster? The answer is yes. So what's that magical stuff? We'll reveal the answer once this video reaches 1K likes. Thank you, just kidding. My colleague Shiva here will be discussing the same with you all. Thank you.
Thank you, Abhishek. All right. So, hi everyone, good afternoon. My name is Shiva, and I work at Google. As Abhishek mentioned, I'm a software engineer, and I maintain gRPC Java. So he just presented some challenges for hyperscale services. What could be the solution? So the solution is proxyless gRPC. Yes, proxyless gRPC. It is a perfect next chapter in the story. So it represents the trade-off between the fully featured sidecar model and a lightweight application integrated model. Modern gRPC libraries have built-in support for the XDS APIs, allowing them to talk directly to the service mesh control plane. The main benefit is the performance. By eliminating the sidecar, you reduce the latency. However, there's a trade-off. The security burden for MTLS and JWTs will shift back to the application. All right, so moving on to the sidecar proxy to gRPC proxyless service mesh comes with many benefits. It reduces the complexity of deploying the sidecar and managing its life cycle. It gains better performance by saving the cost for running a proxy. Also, it removes the bottlenecks in turn. Yeah. It also provides end-to-end security by closing the gap of last-mile security concerns between the proxy and the application. Besides that, you get to enjoy all the benefits with the existing gRPC functionalities that I'll cover in the next few slides. Last but not the least, gRPC has the foresight to use Open Standard API, XDS, to talk to the control plane. As a client library, it is compatible with any control planes speaking XDS. And there are some more advantages like simplified operations, advanced load balancing control, custom backend metrics for smarter routing. That obviously comes with the gRPC features. So let's look at how XDS with Envoy proxy looks like. So Envoy intercepts both inbound and outbound traffic and applies policies to this traffic. This was the start of sidecar-based service meshes. Istio today uses XDS to configure Envoy sidecar proxies. On the other hand, we have XDS with gRPC. API has evolved beyond Envoy, and it is now implemented elsewhere, a lot of places in open source. One such implementation is in gRPC. gRPC now implements XDS, which means that your gRPC clients and server can look up configuration from control plane using XDS without the need of any sidecar. Now, gRPC talking to XDS control plane, the sidecar proxies have been eliminated. And the gRPC library, which is integrated directly into the application, now handles the networking logic. the XDS server communicates directly with the gRPC library. This results in a simpler, more efficient architecture. So we can see in this pictorial representation as well, on the left-hand side is the proxyless gRPC model. This approach eliminates the sidecar proxy, which means one less hop for your network traffic and potentially lower latency for the high-scale systems. Whereas on the right-hand side, we see a sidecar model, which has one extra hop that will in turn affect the performance when compared to proxyless gRPC model. Now let's get deeper into the structure of XDS to give the overall knowledge. There are two main parts in the XDS APIs, a data model, which is a set of configuration, resource types, and the fields that they contain. And there is a transport protocol, which is a mechanism used to get the resources to the client. The transport protocol is a general purpose pub/sub protocol. From the perspective of a transport, the contents of the resources doesn't matter. The gRPC client will have a BiDi stream and can subscribe or unsubscribe to resources. And the server can send updates to the resources when subscribing or whenever they change. So how the XDS resource model looks like in gRPC, the APIs are discovering a collection of resources in a service mesh. X stands for the type of resource. It could be a listener, a route, or cluster, or an endpoint. The URL to connect to will have the listener resource name, which is a virtual host name. In Envoy, this was the address the proxy listened on. In gRPC client, which is not a proxy, we use it to indicate the virtual address to send traffic to. The listener resource points to the name of the route resource, which contains the route map. Based on path and header matching, it can be configured to split traffic between the clusters. The route resource can have retry and timeout configs to use the RPCs via that route. The cluster resource represents a deployment of a service. There can be a separate cluster for each version. The resource specifies the LB policy to use among the endpoints, the TLS security config to use the connection handshakes, the max concurrency supported by the service in the cluster, etc. So an endpoint is a server instance such as a Kubernetes pod. It has an associated health status. An endpoint resource is a collection of all endpoints in a cluster, which can be across localities. And localities can have priorities and weights specified per endpoint to rotate among the localities to send RPCs to. Now let's look at the proxyless gRPC service mesh features. gRPC natively supports XDS APIs, allowing gRPC clients to dynamically discover and connect to a pool of backend servers. The combination of gRPC and XDS enables building flexible dynamic mechanism for distributing traffic across multiple backend servers. gRPC has a strong security support. You can centrally manage access between workloads using client authorization and the MTLS in GKE. Also, gRPC provides capabilities to improve the reliability, availability, and the efficiency of microservices. Circuit breaking can be used to control the maximum number of simultaneous RPCs. It helps prevent excessive load. And then timeout allows you to configure time limits for all RPCs within the mesh. There's this fault injection that provides a way to test your microservices in the presence of different types of failures. We have the custom load balancing. It's a built-in load balancing policies that you can easily configure and start using. Even better, with so the custom load balancing brings your own sophisticated load balancing algorithms and plug into gRPC. So in gRPC you can plug in everything. And also, the observability. So we have recently announced the launch of OpenTelemetry metrics, and you can find user guides and example code for this feature in grpc.io. So my colleague Abhishek has recently implemented some of the observability features within XDS, right? And yeah, retries. Retry can efficiently improve your service availability, and it can be helpful if instances or endpoints are slow or flaky. And it has the other part is the outlier detection. It is another feature to improve network resiliency. The client tracks the success rates of requests made to each backend, and when backends have unusually low success rates over a period of time compared, the clients temporarily stop sending requests back to the backend. So these are some of the comprehensive, this is the comprehensive list of the XDS features supported in gRPC. We are continuously expanding this feature set, and there are more to this feature set. This is a 1-month-old set. Yeah. So, and our commitment is to making Proxyless gRPC a first-class citizen in the service mesh ecosystem. I personally implemented XDS configurable HTTP connect, GCP authentication filter, and many more within gRPC library. And my colleague Abhishek is currently adding more observability features within gRPC. So now let's define how do we use it. So we have a management plane, the control plane, and the data plane. Let's define them individually. So you're probably wondering, how do I get started with Proxyless gRPC? Well, it's actually pretty simple. All you need to do is add the gRPC library to your application and configure it to the XDS server. That's it. You're ready to start building your Proxyless service mesh. It's like getting a new superpower, but with all the complicated training, without all the complicated trainings. Let's talk about the data plane. The data plane is the critical path of user-facing functionality, and therefore have higher availability requirements than management planes, are more performance sensitive, require higher throughput than management plane. The control plane provides policy and configuration for all the running data planes in the mesh. Think of it as a mastermind for the data plane that controls all the traffic and acts as an inspector. Control plane does not touch any of the packets or requests in the system. The control plane turns all the data planes into a distributed system. And finally, the management plane, which is a slow path and configures the control plane. Declarative clients such as Kubernetes operate on the management plane exclusively. This is the slow path where we humans interact with the system. When you are using a tool like Kubernetes to declaratively say, I want my service to look like this. So you're talking to the management plane. It takes your instructions, translates them into the configuration for the control plane, which then directs the data plane. So here is a popular example of how the different planes would translate for a mesh setup, like using Istio. You would use KRMs to declaratively define your infrastructure. The management plane would push config to the control plane, which is Istio in this case. And you have multiple options to configure the data plane of the application. Something I would like to draw your attention is this gRPC. gRPC can work in a heterogeneous environment as well. gRPC applications coexist with other proxied or sidecarless applications. Here is a similar setup in the GCP universe. By the way, GCP is Google Cloud Platform. You could use gateway APIs to configure GKE management plane or use the general gcloud commands. The management plane would then push the configuration to traffic director, which is the XDS managed control plane provided by Google Cloud Platform. Yeah, so let's summarize with some best practices for this end-to-end security with gRPC in Kubernetes. You always need to encrypt, enforce MTLS for all service-to-service communications, automate everything. Manual certificate management is not scalable. Using tools like Cert-Manager or a service mesh is always better. Layer your security, use MTLS for service identity and JWT for user identity. Centralize the policy. A service mesh provides a single place to manage your authorization rules. Always regularly scan your images for vulnerabilities and keep all your tools up to date. So what are the key takeaways from this presentation? First, securing gRPC in Kubernetes is critical and requires a layered approach. You face an obvious trade-off. A Kubernetes approach puts the burden on the app, while the service mesh puts it on the application. For complex multi-language environments, service mesh provides a more scalable and consistent solution for end-to-end security. So yeah, that's all. Thank you. So this was the these are the different ways you can connect with the gRPC team, and feel free to open an issue in any of our repo. And yeah, don't forget to join the gRPC mailing list, so you'll get all the announcements regarding new gRFCs that we make, and all the design reviews. If you want to be part of it, you can always reach out. Yeah, thank you.